there are two factual things to consider here if you wanted to kind of go into the following level of detail. So let us use the 10 legal Penrose tilings on the 12 square inch patch. So we have these 3.6 million animations that we can make. And let us say that some number of these animations are worthless for quasi-particle pattern formation, and they're more analogous to just noisy Dirac sea in vacuum space. And let us say that these worthless number of n states from our 3.6 million animations have about 0 frame savings. But if there are some ordered sets that allow 10% of the frames to be saved, well then we have a higher number of coherent particles that can be formed, because one, we get extra frames to do something with. We're still going to always use the same number of frames. We're going to use what we saved. And and that's because we still have 3.6 million to work with. And number two, a frame savings can save the position of 1 or 2 or 3 or even very large numbers of 20 group positions or positions of whatever your element is that you're using to make patterns with the Penrose tiling set. And that depends on the quality of the ordered set. The savings potential, which is simply our model for energetic potential, becomes very large in certain cases where you have the possibility that one emperor or one way of relating particles, right? So things are oscillating, and quantum mechanically, in our view, we can see them oscillating in these discrete vibratory modes, and with all sharing the same universal frame rate. They can be highly out of phase or highly in phase, and all of those, and where phase is just a general catchphrase for a lot of different correlation classes that we have implied here. So because of these opportunities for frame savings, the quantity of quasi-particles that some of the ordered sets can model are very large, as each frame savings expresses cost-free XYZT coordinate actions for very large numbers of quasi-particles formed of 20 groups per frame, per some set of ordered frames. And so unless we think that right now we happen to be at the universe's epitome of organizational quality in the ordered sets over some quantity, which we're not, well then we should assume that there are higher qualities of order wherein more quasi-particle formation can occur than what we have now in the universe. So this is a computational efficiency principle that serves as a discrete quantum field theory view of quantum thermodynamics. But where this quantum thermodynamics is very extended beyond, electromagnetism into the regime of a foundational potential, which is the position, the 20 group. Or it's general, you don't have to use 20 groups. You could use any element. So that in my other version of this presentation, I just said, let me be sloppy with my language, and instead of working with parallel vector classes, I generalized the word parallel to mean correlated, and it could be angular relationships, phase relationships, T over P correlations between two particles. So that minimizing, so it's a bunch of scalar classes and you want to correlate them. So minimizing the quantity of disassociated relationships is the name of the game, but where also we are dealing instead with a set of parallel scalar classes where parallel here means correlated in a manner that maximizes 20 group savings for the purpose of creating physically meaningful pattern in ordered sets. So consider that we lock ourselves in to some level of frame savings for our 3.6 million possible videos that we can make from 10 Penrose tiling configurations. Now, we would immediately see that we must focus our pattern-generating firepower for quasiparticles on only a small percentage of space in the 12 by 12 animation. You can't have everything easily have coherent quasiparticles. And so most areas of the little Penrose tiling over any couple of our 10-frame, any couple frames of our 10-frame animation would necessarily be dedicated to sort of background noise, where we might use these star decagons instead of our 20 groups here, with star decagons appearing and disappearing with no coherent pattern whatsoever over time. So of course, this is exactly the case with clock patterns and non-clock patterns, which are bosons, made of 20 groups in, say, 100 frames of one of our animations coming from E8. So my notion of an order parameter is an object, or a analysis really, and that gives you a signature, and it searches the vast possibility space of ordered sets to find the ones that save the most 20 groups relative to the total information, or E, being created. But that always depends on calculating your animation both forward and backward in time, because the animation is the energy landscape. And to get quantum statistics, you have to feed the statistical machinery with the information defining the energy landscape itself. And the ultimate quantum gravity theory is feeding that gravitational information, the gravitational energy landscape, and the quantum energy landscape, and it is also feeding them a new landscape, which is the emergent code theoretic landscape, which gets really weird because the probabilities for things in that hierarchical strata of emergent information. Remember, we talked about the 100 angstrom sphere and DNA in the middle. Okay, the probabilities as you get into very complex systems are not typically based solely on on QED type statistics. That things are behaving according to other objectives. And for fun, I gave a presentation with Fong at the top of a mountain, and she had purchased Ray a box of French macaroons. And Ray really likes those things. They're very sweet for most of us here, but Ray eats them up. And he'll do anything to get those macaroons. He will. He treasures them. So then we had Ray at the bottom of a very deep gravitational energy well. And we could also imagine it to be an electromagnetic energy well by putting magnets on Ray, on his clothes, and then sucking him to the ground, right? We're just locking him down. And Ray somehow climbs out of that energy well against all odds, statistically speaking, to pull out of this, the attractor of this energy well and make it to the top of the mountains to get these macaroons, because he has some religious philosophy that eating those macaroons will get him closer to God, right? Abstract, not a statistics of energy wells. And you can get to DNA and its evolved interest in propagating the genetic lineage of a species over very long time durations. And it develops these protein folding algorithms and other things encoding personality traits of children to make them more inclined to get along with people and serve creative and other purposes within a tribe, so that the tribe has long. So the point is from tiny systems to other systems, you will see information at very high levels of emergence acting more and more in a force-like manner, determining the statistical evolution of the system itself. So you simply cannot properly do complex systems physics. And when I say complex systems, I mean what most complex systems theorists mean, which is a complex system starts very simple. Like most systems are complex systems. And you just can't use ordinary quantum mechanics interested only in the energetically efficient time and space propagation of particles. That would be quantum thermodynamics, which is part of our model. And that efficient behavior of particles propagation through space and time to save frames, that is emergent information. It is E, it's not little I. Little I is only the calculations, the frames. It is emergent information, and so the principle of efficient language considers all E. And if you have an early universe situation or some system that's not full of complex systems like us, then the only thing that the PEL is going to do is give you the pattern that is generating all of the energy landscape. It'll give you QED, okay? It'll recover there. But as soon as you start climbing significantly high on the emergent hierarchy, this weird abstract E starts defining the evolution of systems in a more and more profound way until eventually it starts competing with the quantum thermodynamic objectives. Yeah.
So I mean,
oh.
So I mean, it seems to me that you have two competing phenomena. You have something which is more related to the standard quantum mechanical approach, quantum thermodynamics. So essentially, universe wants to save energy, computational efficiency. On the other hand, you have the emergence of very high quantum information,
yeah.
So very higher levels, which is very interesting. I never thought about that. At some point starts competing.
Yes.
In the sense that when you describe Ray climbing the mountain to get the macarons,
yes.
Is really spending a lot of energy.
Yeah.
So it's very computationally inefficient at the level of the code,
yes.
I guess.
Correct.
But is under the action, of this, is following other patterns created by these higher levels of information.
Exactly, and it does so, the PE, yes, that's right, but the PEL requires what Ray did, to be done economically. Now, the problem is, Ray cannot see the cascade of connections. In other words, maybe he gets to the top of the hill, and in so doing, he changes something up there that makes something more efficient for a flower that's going to grow there next spring. Or maybe Ray has this interest of giving these macaroons to his mother, and all these different things over time, some that Ray has in his mind, others that he doesn't. So the PEL implies that it is trying to economically save AB equals P solutions in order to generate the total I, little I plus E, emergent information, which is the sum of all information on the emergent hierarchy, equals big I. So the principle of efficient language is concerned with big I economization. And in very simple systems, all that you have is very low E, which is thermodynamic and particle information at a simple level where they haven't begun to self-organize into systems like us or DNA or other things yet.
Sorry, Ray, but you might never eat those macaroons. Quantum mechanics, actually, Ray is not climbing the mountain. Ray is a quantum creature, so it's a superposition of a ray which stays down in the well, at the bottom of the well, and the ray that is climbing the mountain.
Yes.
Maybe when he eats the macaroni, it might collapse. The ray is in the mountain.
Yeah.
But until you do that, Ray is not eating macaronis. Ray is not climbing the mountain, but Ray at the same time is climbing the mountain, and Ray is eating the macaronis. So quantum mechanically, that's the way I would think of this thing.
Copenhagen quantum mechanically, right? But yeah, that's the way I would look at it that way. I mean, meaning if
see, there are interpretations, there are various things, but what is important that at the end, when you calculate things, they have to coincide.
Yep.
So those are different ways of getting to the same thing.
Yes.
So what I'm saying, maybe another interpretation, but that's the substance of quantum mechanics. Maybe viewed in this way, but the description is this one.
Yes.
In any case, the effect that you measure is this one.
Yeah.
So until somebody sees Ray eating the macaroni, nobody can say that he's eating the macaroni. Nobody can say that it has gone up to the mountain.
Yeah, but so I have a view that's a little bit, you know, similar, epitomized by Einstein.
It's a superposition, otherwise.
Yeah.
Otherwise, it's classical. You see, I mean, you show the wave, which is actually the square of the wave function. I would like to see the wave function. You see, and that's a big difference, because otherwise, there is the risk, which is probably not the case. Probably something that I did not understand. I'm not saying that you're doing this,
yes.
But there is always this risk, which is also in the example of Ray climbing the mountain, that one exchanges, not you, I would say you generally, a student of quantum mechanics may try to confuse quantum mechanics with wave mechanics. So he's losing all the essence of quantum mechanics. So by saying Ray is climbing the mountain, this is not a quantum mechanical statement. Not even Ray is climbing the mountain with certain probabilities a quantum mechanical statement. The quantum mechanical statement is Ray is a superposition of a Ray who is going up the mountain and a Ray who is staying down the well. That could be a quantum mechanical way of thinking.
Right. So
I'm not saying that you're not doing this.
Yeah, yeah. So I'll just share
trying to rephrase and take the example.
So,
sorry, Ray, for your macarons.
I'll give Einstein some credit
Finally,
for.
no, I don't know if I will have the
That's
macaroni.
a problem.
Come on, bring me some.
Now you're gonna.
I don't want
Sorry,
to. I don't want
if I'm
to.
waste time.
Yeah. So I don't want to have a physics that requires, that places too important a role for human observation and the notion.
Okay,
the
so then the
notions.
superposition is there.
So well, let me say I want to say that there is an ontological realism to what Ray is doing through the vast landscape of random walks in some path integral space that was chosen because the probabilities happen, and it doesn't require an observer, as is often discussed. What I want to say is that these AB equals P solutions are observations, they're measurements, they're choices, and they get laid down, and there's an ontological realism. Now, what our model will have to do is we will need to explain the measurement problem, and I will not be able to do that for a little while, but there's some role of human observation that is very bizarre when you consider the retrocausal eraser experiment, double slit experiment predicted by Wheeler, and not proven experimentally until after he died, I believe. And so there's a blurriness for me on any serious disconnect between the experiments, because I'm careful to realize the different interpretations of quantum mechanics. What we have to do is explain the experiments and
So Klee, I think Piero's question is not primarily an interpretational question, or even a question about when the wave function collapsed or the role of an observer. It's more a mathematical question about quantum mechanics requires mathematically requires the superposition principle, however you may interpret it.
Yes.
Yes.
And mathematically what we have here is a probability without, so far, a superposition principle from complex wave functions.
So we had the superposition in the Compton wavelength of the Fongs. So that is a superposition principle there. Now, that still goes out, meaning there is also lesser intense possibilities for similar things like what we had inside the Gaussian distribution of the multiple Fongs. And then I also explained on the lunch break about the meaning that I'm expressing for a probability landscape that is a superposition of all possible paths that the particle can take, and that's a mathematically real thing. And in that space, due to the energetic landscape, which is the relationships which must tie back to the principle, this economization principle of least computational action, within that space there are different probability amplitudes and such that what actually happens have the higher probabilities on that set of paths of Ray getting up the mountain that were more economical.
A comment, he's discussed some states where the building block state is building from this principle of efficiency language. So you have some first principle way to build your state. So the wave function should be think of the sum of all these states. But to build the wave function, we need to build the small amplitude for each state. Then you sum over to get the idea of the wave function. And another point is that he has this idea that the principle of efficiency language and the principle of least computation.
Yeah.
The second is incorporating the principle of efficiency language.
Yeah.
Yeah.
Okay.
No, okay. It's okay.
There's so much more. Yeah. I feel that if I were you at this stage, I would. There's so much that I can layer in, not only by the end of this presentation, but with more meetings. It's there's things that I haven't expressed yet that may cause questions that can be answered even at this early stage. But our wave form is very much related to pi. I mean, it's curvy. It has helicity. It is clear from some first principles why the mathematics implies waveform in general, and we'll get to that and try to make it connected even to general relativity after lunch. All right, so our universe is all right. Well, so our universe is still very, very young. We're 1.4 solar lifetimes old at this point in the visible universe. And so in a way, it's just getting started. So at this stage, the patterns that are encoded into the OA to OB parameter are instructing the E8 random walk code to focus on the emergent information of particles, planets, solar systems. The model predicts the number of quasi-particles in the universe is increasing as negentropy continues to increase. And again, remember, there's rich informational deltas in these various legal Fibonacci chain iterations when you do the Fourier transform and then do multifractal analysis or wavelet analysis on these patterns. So there are derivative analyses in the higher dimensional tensor network animation that I speak of. That's one of the analogs in 3D and 4D that we described earlier. And I don't know what those analyses are. I just know that they're there. So I'm fairly certain there are special relationships between the clock cycling and the forward propagation that relate to these two analyses and a certain tensor network formalism. There are ideal relationships between the particle's internal clock, which is more complicated, and it creates a waveform out of it, a waveform that's integrated over time on the ruled surfaces that come out and drop in density. And then it's forward propagation, which is also wave-like if it moves helically forward, and that also creates a less complicated waveform, and then the two together, integrated, create this rich wave function of 20 groups all over the place, forward and backwards in time, and how the particle behaves is based on that landscape of these, what we can call gravitational energy quanta, potentials. All right, so we should cover one more simple math fact to understand our sum over histories idea before we get more into the first principles of our fermions and its computational energetics. And we'll do it in 1D so you can get the principle. Consider a one-dimensional quasicrystal, like a Fibonacci chain, that is short. Short enough that there are only 10 different permutations. So you could order those little Fibonacci chains again in a lot of different animations. But if you take the superposition of all 10 of them, you would get a quasicrystal with points that are closer together than any of the individual 10, right? Because they're all different, but you superimpose them and you get a superposition. And we call that, that's called in the literature, a deflation of the first set. And it kind of deflates according to the golden ratio power series. And how you deflate something on each scale, you have options. So you can deflate it this way or that way. Another way to think of this is to increase the size of your empire window to the size, if they're Fibonacci chains, your higher space is just a checkerboard. It's the Z2 lattice. So you increase the window, the projection window size, and you simply project all possible positions of the empire window. So the way I'm starting to think is that we move the empire window around within a boundary and we only project the empire. And so if I project all possible empires by moving my empire window, and I take only the possible ones that live within the boundary of this bigger window, then I get my superposition state of all my points, my potentials. So in this case, there will be 10 different empires projected to 1D and just superimposed. And the sum over histories of quasi-particle patterns are the 3.6 million ways to create ordered sets from the 10 Fibonacci chains by simply turning points on the superposition quasicrystal on and off. By turning them some off, you create an inflation. So to memorize that, think of drawing 10 dots on an inflated balloon, and if you inflate it more, you create bigger spacing, and if you inflate it less, you create closer spacing. So this same principle applies to all of the ways that you can move the compound quasicrystal empire that has the rotational center or emperor of the QSN in it. You can move it around in a lot of ways, and you can take the superposition of all ways. The random walk quasiparticles within the 3.6 million animations have different probability amplitudes based on the 20 group computational economization thing that we've been talking about. So there's a lot of confusion about quantum mechanics. Is a quantum wave function a physically real dynamic object like a pilot wave? Or is it just a convenient statistical tool that does not possess spatiotemporal geometric realism? Does a virtual photon in the electromagnetic field around an electron have geometric realism? Or is it just a non-ontologically real abstract modeling idea? And how about a particle in Dirac C? Is it real? Is it virtual? Dirac would say it's real, right? And his model says it's real. So imagine that the electromagnetic field around an electron is composed of patterns made of empire waves built of 20 groups. And let's call these virtual photons because 20 groups in the empire wave around the clock are not the clock, right? So the empire wave around it is not the clock, but they are controlled by the clock. And they control the clock, right? Because they guide the clock, and the clock defines them. So let's pretend something like Bohm's pilot wave is real, just as we can suppose virtual electrons that make up the electromagnetic field of the electron clock particle are also real. So Bohm's pilot wave accomplishes exactly what Schrodinger's wave function does. It just tells us statistically what the probabilities are for getting a position measurement of the clock particle at some time too. So let us first use Schrodinger's formalism, and let us take an electron and create an angstrom volume around this electron. And let us discretize this space into some quantity of xyz coordinates. So let's say we have 1 million of these xy coordinates evenly spaced around this angstrom volume, around this electron. And let us ask the formalism to give us the time to probability amplitude for measuring the clock or electron at every single one of the coordinates and then plot them in a computer. What would that look like? And would it have rich substructure, or would it be a blurry thing, like fuzzy? Well, it does have substructure. So this is not the projection of a discretized Hopf fiber distribution of a 3-sphere to R3. It's actually a sophisticated quantum mechanical mapping of the virtual photons of the magnetic field around an electron. If we add in the electric field component of the EM field, it would increase the complexity a bit. Now clearly, the probability amplitude distribution for position measurements of the electron in vacuum are exactly defined by its own energy landscape. That is, the virtual photons of its dynamic electromagnetic field. This is the quantum statistics of electron self-interaction. So as Marcelo agreed with me on, the virtual photons of the EM field, the Bohm pilot wave, and the Schrödinger equation are all equivalent labels for the same object, which just gives you the quantum probabilities for position measurements at some time too for the electron. So when I try to non-locally just visualize our empire wave field, I always see a pattern almost exactly like this every time. Our empire wave equals, it is the EM field, it is the pilot wave, and it is a quantum wave function. So in a clock made of 20 groups, then what are the patterns of empire rays that are not part of the clock and that have ruled surfaces over a full clock cycle? They are certainly not fermions, and they are not exactly particles, although there are models that say they are made of virtual photons, but not lasting ones, not coherent over time. And they are coherent, and they're orderly as a collective group, or are they like virtual photons or the photons in the Dirac analog that logically also exist in our noise, the noise between order that we have? Well, of course they're orderly, right? They have structure, just like the emperors that define their ruled surfaces. This has rich structure because the clock has a complicated internal pattern. It has a complicated integration with its helical forward motion, and therefore the empire waves, the integrated ruled surfaces, forward and backward in time, form a very rich and quite beautiful pattern over time of gravitational or just potentials. So, but they're not part of the clock, so they're like a discretized field of magnetic flux tubes, where the flux tube has substructure, just like in other theories where the substructure of the flux tubes is this notion of virtual photons, virtual energetic objects. All right, so in our case, they're made of the same objects as the clocks are made of, just 20 groups. It's 20 groups all the way down so far. The PEL demands higher probabilities for the clock to be at locations at time 2s that relate to its own EM field of 20 groups around itself and the 20 group fields of other clocks. The PEL places higher probabilities, as well as the 20 groups in the noise. So the thermal bath of the quantum energy potentials around it, this will also interact, although less profoundly than its own self-interaction, and secondly, the interaction of other empire waves from other clocks around it. All right, so it puts a higher probability of AB equals P solutions that give these free 20-group positions without having to do as many computations or E8 random walk projector steps or the matrix or other algebraic equivalencies thereof. So there is a statistics that I'm claiming that is waiting for us to uncover in this model. I mean, even if we pick a non-physically realistic clock following everything that I'm saying so far, there will be a probability landscape that comes without contradiction. Doesn't have to, I'm not claiming it's going to be physically realistic, and I don't even expect it to at first. So, but we must discover a computationally feasible OA to OB feedback loop formalism. And we will not be able to do our physics without that, because if we just write down a bunch of equations, we'll just be more people doing gauge symmetry unification physics. And that would be in and of itself, to get the correct gauge symmetry unification model, that would be wonderful. But we want to simulate things that using this new subquantum mechanics. And to make the world believe us and to convince ourselves, we need to do a lot of computational physics from this point forward. And we need the tensor network formalism. We have to move away from geometry. We need that. Because without that, I'm just doing this hand-waving thing, saying there's this magical thing in the universe that just picks the shift vector actions. All right, so we will not be able to do physics without it. So quantum mechanics gives the statistics for particles relative to the energy landscape around the particle. The energy landscape in the canonical models are made of virtual photons. Now, for a single electron in vacuum, as I said, its EM field is the dominant energy landscape, providing, in some sense, a model that is essentially an ontologically real guide wave or pilot wave, in terms of its own self-interaction statistics. So we call our ontologically real EM field and pilot wave, we just call that the empire wave. And it doesn't exist in a single frame. All that exists are these relatively boring radial beams of 20 groups that come out. That's boring compared to what happens when you integrate it over time and you get the ruled surfaces that are very complicated and beautiful. So don't mix the term empire and empire wave. Just recognize them as very different things. Of course, the empire wave is built of empires. All right, so it's not an empire, it's the integrated ruled surface of the empires of at least one full clock cycle of the particle's clock. So you don't want to call it the full calculation of the empire wave until you've done a minimum of one clock cycle. Then, because without that, you wouldn't have the full symmetry. And it's a statistical object as much as it is a physically real thing. So because of the Gaussian distribution of the magnitude of 20 group savings, where we have higher probabilities for 20 group savings in some parts versus other parts, okay, most real world T over P ratios, where T is generally much, much higher than P, right? Because most fermions, other than, most massive particles other than neutrinos are moving at very small fractions of the speed of light, which means that in their T over P ratios, the vast majority of shift vector actions or graph connections in the physical space are dedicated to enormously energetic internal clock behavior.
I have a question, Klee. This empire wave, it's real and has this Gaussian distribution, right?
That's right.
That's right.
So it's not strictly a Gaussian distribution. It's just roughly speaking.
Yeah, indeed, this was another question because it seems to me why exactly Gaussian?
Oh no, I'm not. It's one slide I wrote Gaussian-like.
Gaussian-like. Okay,
yeah.
good. But so from the point of view, it will be what I will call squared wave function. I mean, no. So it's not a real wave function because wave function is complex, right?
Yeah.
So can you relate some of your framework to something which is a priori with respect to the empire wave? So something which I mean, the empire wave is the absolute value squared of something else.
Yes.
What is this something else in your model?
So far, I only presented this idea to our internal group about 10 days ago. So it's a brand new idea, and I estimate that the average comprehension before this presentation, averaging every person, could be 50% of the comprehension I have of it. So my comprehension is only my comprehension. It's a story, but I have a lot of detail and back story on the story. And so what my plan was is to sort of get all of them to homogenize at about the same level of 85, 90% of what I am trying to say, and then beat it up and take it apart and find out how to, and whatever is left after beating it up are the things we have to vet with calculations, equations, and computations. So the answer is yes. In this story today, I want to develop a physically realistic wave function where we square the amplitudes and we follow some directions from other formalism to bring, connection.
Maybe I have a positive answer. So the probability density here is the density of finding truth saving along the axis of motion.
20 group saving.
20 group savings. And but if you look at the circle in the plane which is perpendicular to the axis of motion, we have a phase. So I think that this phase is the phase that you have to add to build the correct wave function. And effectively, here we have, so it's a complex number.
So where does the phase come from? Sorry.
The phase is in a circle, in the cylinder. In fact, this is a 2D projection of a cylinder. And inside of this cylinder, you have circles, and the 20 group saving are in this circle. So they also have a phase if you compare them to this axis of the motion.
And discrete phase set.
Discrete phase.
With a tenfold symmetry.
So it seems you might reconstruct something which is actually a wave function.
Yes.
I mean,
I
a
think
complex wave function.
I think the way that you could think about it is that they're looking at the moduli space of the 20 group, and you're computing over tilings of this moduli space because it's.
But the moduli space will be this discretized circle. So it's.
It might be a coset with respect to H4. Might be a H4 coset.
I mean, yes. So, I mean,
Okay.
Yeah, but it's
okay. Anyhow, you have some search for the face. That's very important. Yeah. Okay.